whole purpose of section 8.1 was just to remind you of what a complex number looks like. How do you add, subtract, multiply, and divide complex numbers? So a complex number, remember, has a real part plus or minus some imaginary part. And that's where the number I kicks in. The number I is an imaginary number, meaning the square root of -1. So you have a complex number in the form of a plus bi, where a is the real part and the bi is an imaginary part. Any number that you can think of right now, any number that you can think of is a complex number. It is. So examples. 3 plus 2i is a complex number. Negative 4i is a complex number. You'd have to think of it as 0 minus 4i, right, if you want to think complex number. But like I said, any number that you can think of, like 7, is that a complex number? Yes, because you can write it as 7 plus 0i. The same number, right? So any number that you can think of can be written as a complex number. How do we add, subtract, multiply, and divide complex numbers? Let's take two complex numbers like 2 plus 3i plus 3 minus 2i. Anybody remember how we add those together? We simply do what?
Add the like term.
Combine like terms. Treat I like a variable. You add those together, add the real parts together. 2 plus 3 gives you 5. Positive 3i plus negative 2i is positive 1i. So there would be the sum of those two complex numbers. You get another complex number. Subtraction's the same way. With multiplication, you need to be careful because you have to recall that since I is the same thing as the square root of -1, if I square both sides, I squared ends up being -1. So you got to watch out that when you multiply complex numbers together, when you ever see an I squared, you have to remember to change that to -1. For example, let's multiply the following two complex numbers together. 2 minus I, and let's multiply that with 4 plus 2i. Now, what do you think I'm going to have to do here if I'm going to multiply these two binomials together? You're going to use the FOIL method. First outside, inside, left. Again, just treating like as if I was a number. So 2 times 4 gives you 8. Outside terms gives me a positive 4i. Inside terms give me negative 4i. And last times last. Negative I times a positive 2i is a negative 2i squared. Now notice my inner terms cancel each other out. Doesn't always happen that way, but in this case it did. So we end up with 8 minus 2 times I squared. But wait a minute, I squared is -1. So our final answer ends up being 8 plus 2, or 10. So yeah, believe it or not, when you multiply those two complex numbers together, you get a number that's a real number. Okay? Which leaves division. And division, do you guys remember when working with radicals, you had to rationalize the denominator? You were not allowed to leave a final answer like 3 over the square root of 2, so you had to write this as 3 root 2 over 2, right? You can't leave I in the denominator for the same reason. I is the same thing as the square root of -1. So if you leave an I in the denominator, it's the same thing as leaving a square root in the denominator, right? So you multiply top and bottom. In this case, you could multiply top and bottom by I. And that would give you 3i over what? -1, I squared. So your final answer would be -3i. If your denominator was a little bit more more challenging than just I, let's say your denominator, and then you can start viewing this as dividing two complex numbers. Let's say you want to take 2 minus I and divide that by 3 plus I. Well, you're going to choose to multiply top and bottom of this problem by what we call the conjugate. If 3 plus I is your complex number, then 3 minus I would be the conjugate. And we're going to multiply top and bottom by the same thing so that we're not changing the value of the problem, right? We're just simply changing what it looks like. And if I were to look at the denominator, look what happens. By using the conjugate, right, your i's will disappear. 3 times 3 is 9. What happens with outside terms, inside terms, right? They cancel each other out. You get a positive 3i, you get a negative 3i, gone. And finally, positive I times negative I is a negative I squared, which ends up being minus negative 1. So we end up with a 10 in the denominator. It's okay to have an I in the numerator, which is what happens. 2 times 3 is 6. Outside terms would be negative 2i. Inside terms would be negative 3i. And last times last is a positive I squared. Positive I squared is negative 1 with our existing 6 gives me a 5. Negative 2i and negative 3i make negative 5i. And you just got to make sure your final answer is in lowest terms. No, we can divide everything by 5. So we end up with 1 minus I over 2 being your answer.
But I squared.
I squared, this became a negative 1.
Okay.
And the negative 1 with this 6 is where that 5 came from. So folks, this was all that section 8.1 was showing you. Exactly what is I? I is the square root of negative 1, and how to add, subtract, multiply, and divide, which I think you've had in another math course. Okay? Questions before I keep going?
What's 3i?
Excuse me?
3 i's?
What do you mean, what's 3 i's?
2i is negative 1. What's 3 i's?
Negative 1.
What's 3i?
I think it's
No, what's I cubed?
I cube, yeah.
I cubed. Good question. How about I cubed? Well, think of that as being I squared times I, right? And I squared is the same thing as what?
Negative 1.
Negative 1, and negative 1 times I is simply negative I. So I cubed is the same as negative I. How about I to the 4th power?
1.
I to the 4th power, you could think of as being I squared times I squared. Each of those is negative 1. Negative 1 times negative 1 is positive 1. What's so funny, Hannah? You're laughing at I squared for some reason. Okay. It's just stupid. Can I move on? Now, how does this apply to trig? The opening paragraph was what I mentioned earlier. It says, unlike real numbers, complex numbers cannot be ordered. You cannot line complex numbers up from smallest to largest. Can't be done. So we got to come up with a way to organize or illustrate them, and that's by using a graph. So to graph the complex number such as 2 minus 3i, we modify our existing xy grid to a what's called a complex grid. So we have the x-axis be the real axis, and we have the y-axis being the imaginary axis. Okay? And then this is called the complex plane. So if you want to graph the number 2 minus 3i, 2 is the real part, so we go over 2 units. Right? So I want you to start thinking of this now in terms of x plus yi. X is 2, y is negative 3. So we went to the right 2 and we go down 3, and this vector corresponds with the graph of that complex number. Okay? And guess what? The parallelogram rule holds true. If you were to take 1 plus 3i and you want to add to that the complex number 4 plus I, you and I just got done talking about how do we add complex numbers together. We add the real parts, we add the imaginary parts. What do we get? We get 5 plus 4i, which ends up being the diagonal vector. You see that? When we add the two blue vectors together, we get the red vector, which is the 5 plus 4i vector. It's pretty amazing. Now I actually get to the major part of this section, and we want to start talking about a different form of a complex number. And some books call it the trig form of a complex number. Some books call it the polar form of a complex number. And all this section is, the only intentions of this section is practice on you changing it from one form to the other. Okay? Why do this? Well, what you're about to see in the upcoming sections, can you guys imagine how long it would take if I gave you a problem like, I want you to take this complex number, 2 plus 4i. Take that complex number, and I want you to tell me what would the complex answer be if you were to raise this to the 12th power. What is the only way right now you know how to answer this problem?
Multiply it all out.
Multiply it all out. You'll start with 2 of them, right? Multiply those 2 together, get an answer. Take that answer times another one. Take that answer times another one. Take that answer times another one. And do that 12 times. That's really the only way you know how to do that problem. There's a much, much, much faster way if you momentarily take the complex number, convert it to this other form, which we call the polar form. Now it's a lot easier to raise that to a power, and then convert it back to this form if you have to. See what I'm saying? So the purpose of what you're about to see, folks, is to allow you to not only take a complex number and raise it to a big power, as you're going to see in about the last section of this chapter. A French guy by the name of de Moivre's theorem, I think it's called. You're going to learn how you can take the cube root or the square root of a complex number as well. Okay? That's a preview of coming attractions. Right now we're just going to practice converting it from one form to the other. So what we can do next is tie in our information about vectors. We learned this in a couple of previous sections or chapters. We know that this point P right here has the coordinates r cosine theta, r sine theta. And since this distance we call x, and since this distance we call y, we also know that the tangent of this angle is y over x. We also know if we need to get r, and these are the same fundamental theorems or formulas that we learned in other sections, just by using Pythagorean theorem, right, we can come up with r. Okay? With me so far? So, if we start with what's called the rectangular, this is the form that we're currently familiar with, you know, like 2 plus 4i. This is what we would call the rectangular form of a complex number. We're about to convert this into the polar form of a complex number. Well, what was x the same as? X is the same thing as r cosine theta plus, what's y the same thing as? Y is r sine theta, and we're going to multiply that by I. So it's I times r times sine theta. And we're going to factor an r out. We have r times the quantity cosine theta plus I sine theta. And right there, folks, right there, this is what we would call the polar form of a complex number. Now, some trig books, I'm glad ours does this, not all of them do this. Some trig books have shorthand notation for this whole thing. And that shorthand notation comes from this value. Oh, let's not try to highlight with a black magic marker. This value this letter, this number, and this letter, and this angle. So if you see the shorthand notation r cis theta, that is referring to the above statement. R cis theta is shorthand notation for the polar form of a complex number. Okay? Now we're going to simply convert from one form to the other for a couple problems. One direction simple, the other direction is a little bit more challenging. So here you're given, right? Here you are given the polar form. And again, what would the shorthand version of this look like? The shorthand version would look like 2 cis 300. I'm just going to write it that way just to give you more exposure to the shorthand notation that your book uses. Now, how do I convert this to the rectangular form? Well, 2 times the quantity cosine 300 degrees plus I sine 300 degrees is the same thing as 2 times the cosine of 300 degrees plus 2 times I times sine 300 degrees. And 300 degrees is a quadrant 4 angle where cosine is positive and the reference angle is 60 degrees. And what's the cosine of 60 degrees? 1/2. So this becomes positive 1/2. So we have 2 times 1/2 plus, same thing, sine, however, right? Sine, however, is in quadrant 4, sine is negative, and the sine of a 60-degree reference angle is the square root of 3 over 2. Negative square root of 3 over 2 since we're in quadrant 4. So what we have over here on the right-hand side is technically I times 2 times negative root 3 over 2. And let's clean this up a little bit. 2 times 1/2 is 1. Over here we're going to end up with a negative value, so we can write this as minus. 2's cancel out, and we're left with an I root 3. And right there, folks, is you're back to rectangular form again. Here is your x plus yi, right? X is 1, and y would be negative square root of 3. I's I. So there's an example where polar to rectangular, that's the easier of the two, by the way, because you're just simply taking the sine or the cosine of whatever the angle is that you're given. Folks, if the angle that you're given has a nice reference angle, special angles again, 0, 90, 180, 270, 30, 45, 60, then you're going to probably be expected to give final answers as exact answers. If the angle that you're given does not have a nice reference angle, then use your calculator, which I'm going to remind myself right now. I better check to make sure it's in degree mode, because I'm not letting that happen again.
Are you sure it's this class?
And I think I used this in the last class, so it ought to be okay. Mode. Yeah, we're in degrees. So moving on. Here's an example where we went from polar form, converting it to rectangular. Do you guys have any questions with that? And again, I've already answered. Why do we need to know how to do this? For an upcoming section where it's going to be a lot quicker and easier for you to take a complex number, raise it to a power, or to take the root of a complex number. Now we're going to go in the other direction. Now I'm going to give you a complex number in rectangular form, and we want to convert it to polar form. So let's take a look at A. Again, I want to remind you that standard form, the general form for a complex number, we got to be thinking x plus yi. So I compare x plus yi with negative root 3 plus I, and I pick off these couple of pieces of information. We know that x would equal what? X is equal to negative square root of 3. We know that y is equal to what?
Square root of -1.
Nope, nope, nope. Y times I. What are we multiplying by I right here? 1. So y is 1. With those two pieces of information, let's figure out which quadrant that we're in. Because if x is negative and y is positive, we're in quadrant 2. Okay? So you need to imagine this ray or this vector coming out here in quadrant 2. We know that the x component, the horizontal component, is negative square root of 3. And we know that the vertical component is 1. We can now find out what r is. Here's r. Use the Pythagorean theorem. R would be square root of negative root 3 squared plus 1 squared. R is 2. Because you end up with the square root of 4, right? R is 2. There's two things I need, right, for the polar form. I need r, got it. And what else do I need?
Degree.
Theta. And I know that the tangent of this angle theta is y over x. Y over x. 1 over negative root 3, which if you were to rationalize that is negative root 3 over 3. Does anybody remember the reference angle? The reference angle that has a tangent of root 3 over 3.
30?
30 degrees. Is that a good guess?
No. Yeah.
So quadrant 2, 30 degree reference angle. This angle is the one I'm after, would be 150 degrees. Now I have everything that I need. How do I write my final answer? Here's the polar form. The answer to letter A would be, remember it's r parenthesis cosine theta plus I sine theta. You'll write 2 times the quantity cosine 150 plus I sine 150. Or shorthand would look like what?
2 CIS 150.
2 cis 150. Good. There's the polar form of that complex number. Make sense? That's the process you'll use all the time when you want to convert a rectangular form to polar form. So B, I'm going to let you guys try on your own. B says take the complex number negative 3i and convert it to polar form. And don't make a wild animal out of this one. I'll give you some advice. You need to be thinking negative 3i is the same thing as what?
YI.
0.
Good. 0 minus 3i. So x is 0. Y is negative 3. I'll let you go from here. Come up with the polar form. This one's actually a lot easier than the last one. X is 0, y is negative 3, puts us right here. So we know right away that the angle is 270 degrees. And right away we know that r is equal to what?
0.
No, not r. Yeah, you're going 3 units. Yep, from there to there, r is 3. So you can right away write the polar form. 3
CIS.
cosine 270 plus I sine 270, which you could write 3 cis 270. You may also be asked to write your answer in using radians, so you'd have to simply over here you can write it as 3 cis 3 pi over 2. What do you mean?
Like,
Tangent.
to find theta, like we did the other one.
To find theta?
Is y over x, which would be -3 over 0.
That's because remember the tangent of that angle is undefined. That's why. The tangent of 270 is undefined because you end up dividing by 0. So there's no function on your calculator where you can be like arc tangent undefined angle. I mean, yeah. I think to get the angle, I think the author expects to get that angle. You simply look at your picture and say, since my point is located right there, it has to be a 270-degree angle. Okay? All right. To finish up, I simply want you to take those two and convert them to the other form. So A, you want to convert that to rectangular, and B, I want you to convert that to polar. Letter A, we'll take 6 times the cosine of 115 plus 6 times I times the sine of 115. And the 115-degree angle isn't one of our friendly angles. It doesn't have a friendly reference angle. So we're going to simply ask the calculator, hey calculator, what is 6 times the cosine of 115? Calculator's in degrees. And we get -2 let's go 3 decimal places, -2.536. -2.536. Then we'll ask it to take 6 times the sine of 115. Don't involve I, you need an I in your answer. 6 times the sine of 115, 5.438. So it's positive 5.438 I. So there's simply your answer to A. All right? B, a little bit more work. Now we're going to convert polar to rectangular. I see that x is 5, and we see that y is equal to -4. That puts us in quadrant 4. So the horizontal component's +5, vertical component -4. What's that make R? Well, that's
Root
25.
41.
What's that?
Root 41.
Square root of 41. Right. 5 squared, 25. 4 squared, 16. Square root of 41. Now we need to come up with this angle. We know that the tangent of that angle is -4 over 5. And again, not a friendly angle. Got to ask our calculator. Hey calculator, what angle has a tangent of -4/5? Now before I press enter, remember that inverse tangent. What 2 quadrants am I working in? 1 and 4. So this is either going to give me a quadrant 1 or a quadrant 4 angle. I can't really write theta in terms of a negative angle measure, so we got to simply take 360 degrees, subtract off previous answer, and put this in terms of a positive degree angle. So our angle is, that's not right. I didn't want
Answer
to.
is negative.
Yeah, I wanted to take 360 minus, not minus negative, because then it added it on. It's 360 minus 38.6598. That's enough. We could throw the 1 in there yet. But the angle that I'm after is 321 degrees, 321.34 degrees.
Can't you find out with sine? Like use a sine and say use tangent. Tan.
Now that you know R, you could. Right, now that you found R to be the square root of 41, you could use one of the other functions as well. It's completely up to you.
Okay, so you know how to use tan.
So what's my final answer? In both forms, we would have R, square root of 41, times cosine 321.34 degrees plus I sine 321.34 degrees. Or the shorthand, square root of 41 cis 321.34 degrees. There's your polar form.
Just out of curiosity, why can't you use a negative angle?
You could, yeah, you could write it that way.
So I mean, in x minus yi, there's a lot of negatives there.
Yep, you could. You wanted to write your answer as negative, whatever that was. You're just not going to see that in the back of the book. All of the angles they give will be a positive. And actually, in some cases, they'll say that your answer, theta, has to be between 0 and 360, which would throw the negative out. We know it's the same angle, but they might specify they want theta to be from 0 to 360. Okay. That's enough